Hello, my name is David Thompson. Thank you so much for having me be a part of the Square Bamboos seminar series. And I'm going to talk to you today about the superformula and model quantum systems as tools for learning. I'm an application scientist at the Chemical Computing Group at CCG, and for almost 30 years, we've made a molecular modeling platform that is widely used in the pharmaceutical and biotechnology industries. I'm thrilled to be at this fabulously cross-disciplinary discussion, and I'm excited to share this work. I'm doing so very much in the spirit of transcending boundaries, and as you will hear, this is a pretty warts and all story of my journey so far with the superformula. Here's an overview of what to expect from this work. As you'll learn shortly, I came to this quite randomly, so I want to orient the work in curiosity. Curiosity is important for a whole host of reasons, not least of which is that it's motivational in nature, which is useful both personally and professionally. I'll introduce you to how I found out about the superformula, what I subsequently learned about the superformula, and then we'll talk a little about model quantum systems, why they're important and of interest, before getting into the bulk of the presentation, which introduces a novel confined electronic system. Then I have a fun little story about what happened next before making some concluding remarks on a Danish polymath. Before I get cracking, I do have this to share. So my family and I were in Taiwan in the summer of 2023 and had an opportunity to visit a bamboo forest in the Alishan township in the mountains. On the left here, you have a picture of some square bamboo, and on the right, just how pretty bamboo forests are. So firstly, some general words on curiosity, a trait of great importance to individuals engaged in cross-disciplinary pursuits. Curiosity is a motivational state that drives information seeking and exploration. While some people are more curious than others, anyone's curiosity can be triggered at any time, and as such, curiosity can be considered malleable. There are validated measures to assess your own curiosity, should you be interested. I seem to be a reasonably curious person, and many of my fondest scientific memories are those things that started out of, I wonder, type trains of thought. Now, an uncle gifted my family a Commodore VIC-20 in the early 80s, and while I assume my parents hoped that I would become the next Clive Sinclair, I was less interested in the fact that I could manipulate it programmatically, and instead initially fascinated by the fact that this thing could play games. I could interact with it in a wonderful way, experiencing a story of someone else's design. In the beginning, with the rudimentary graphics, this was quite an exercise in imagination. This is actually the first game I remember playing, Shamus on the left here. In the middle, we have Super Castlevania 4 for the Super Nintendo, arguably the greatest home console ever, and then the near-photorealistic Rise of the Tomb Raider for the PS5 on the right. This in the space of my lifetime, which is extraordinary, and the interplay of increasing video game sophistication and technology development have fascinated me from an early age. So how did my curiosity land me in front of you all engaged in this work? Well, in 2016, Hello Games, a relatively small video game publisher based in the UK, launched No Man's Sky, a space exploration game for the PS4. No Man's Sky is vast and consists of an algorithmically generated universe containing quintillions of unique planets, flora and fauna. As a lifelong gamer, I knew a little bit about the game, but there's just wonderful overview of the company, the game, and its mission in the New Yorker that really caught my attention. As part of the New Yorker profile, the developers discussed their use of something called the superformula that enabled them to create such a remarkable variety of environment as part of the game. It was the description of the superformula and how foundational it appeared to be that piqued my interest and aroused my curiosity to learn more. I proceeded to jump onto the internet, and here is a super high-level summary of what I found. This is, of course, all very familiar and rudimentary for this crowd, but new and interesting to me at the time. The superformula is itself a generalization of something called the superellipse. The superformula was pioneered by Johann Gillis in 2003 in an American Journal of Botany paper as a, quote, generic transformation that unifies a wide range of natural and abstract shapes, end quote. There's a very general form of the superformula that is expressed in polar coordinates, but I was immediately drawn to specific cases that can be simply expressed in Cartesian coordinates in terms of three parameters, A, B, and N. Here we see some examples of regions defined by the superformula as a function of n for constant a and b. For n greater than 0 but less than 1, the region exhibits concave sides looking like a star. For n equals 1, we see a rhombus, with the corners determined by A and B. For n greater than 1 but less than 2, we see a rhombus with the same corners but with convex sides. And for n equals 2, we have an ordinary ellipse, and if A equals B, a circle. For n greater than 2, this looks like a rectangle with rounded corners. All very familiar and rudimentary, as I've said, for this crowd, but new and interesting to me at the time. Further descriptions of the shapes are presented in Dr. Gillis's paper, where it's clear that it's possible to generate a bewildering set of shapes and features. And then on the right-hand side here, I have a screenshot of how this manifests in the game itself. Now, as a graduate student many years ago, I had the opportunity of working on model quantum systems. The canonical model quantum system is that of a particle in a box. The exact appearance of this model is somewhat hazy, but the earliest reference reported in the literature is in a textbook from the physicist Sir Neville Mott, who described the infinite square well. The problem of a particle in one dimension trapped between two impenetrable walls permits a quantized set of eigenfunctions and associated eigenvalues. This simple conceptual model is a tool for pedagogy that is widely used still in physics and chemistry courses at both the secondary and university levels, and introduces the students to the concepts of confinement, quantization, and degeneracy, all of which are of importance in navigating the thinking of quantum phenomena. The simple one-dimensional particle in a box problem has a nice closed form expression for the eigenvalues of the system, and because of the geometry of the problem, the solutions can be generalized to higher dimensions. Here we see the simple expressions for the rectangular, square, and circle particle in a box problem. Now, single particles are interesting, but things get really fun when you have multiple electrons. I sometimes describe chemistry as the science of understanding how electrons interact with each other. My Ph.D. supervisor explored the solutions to the problem of two interacting electrons in a cube, and I was astonished that this was published in the year 2000, because as soon as he mentioned this work, I felt quite dim for not having thought of putting more electrons inside the confining geometry. During my graduate work, I extended his work to the sphere, and then for more than two electrons at a variety of different levels of theory. While as described, these systems are unphysical, they are interpretable, tractable, and permit the exploration of electron correlation as a function of the tunable parameters defining the geometry of the confining geometry, and can be explored at different levels of theory. Doing so allows us to systematically explore how different theoretical approaches account for different elements of how the electrons are interacting. Several other researchers have contributed to understanding these and similar systems, and I call those out in the references here, and the defining work is presented in reference 15, which represents a significant contribution to the understanding of electron correlation for a whole range of systems. Indeed, Luce and Gill made several contributions regarding several model systems, which is why I pay close attention to their published work. This in turn led me to an archive posting describing an abstract chemistry in one dimension. Note the date of this publication, which coincides with my reading of the No Man's Sky profile in the New Yorker. While the theoretical models themselves are unphysical, there are some experimental systems that demonstrate particle-in-a-box-like phenomena. These are often used in an undergraduate teaching laboratory setting to reinforce quantum principles and have students engage in practical experimentation and measurement. Using nanotechnology and semiconductor fabrication techniques, it is possible to construct devices with a known and well-defined number of electrons within a specific spatial region. These quantum dot systems are sometimes referred to as artificial atoms and provide an excellent introduction to both nanoscale physical systems and their underlying quantum mechanics. A particularly interesting nanostructure is that of cadmium selenide. These are nanocrystals which can be readily synthesized in a university laboratory setting. These will have the same Wurtzite crystal structure as bulk cadmium selenide, but will consist of just hundreds to thousands of atoms. These structures can be grown to a desired size, and as their size increases, the energy of the first excited state decreases, which is in quantitative agreement with the particle-in-a-box model. Thus, they serve as accessible experimental systems that link theory and tractable experimentation. Last year saw the reporting of the synthesis and characterization of a physical manifestation of a 3D particle in a box, perfluorocubane, which was subsequently selected as one of the molecules of the year by the American Chemical Society's Chemical Engineering News. Okay, so let's scoot back to 2015. All of these contributing factors previously described, the superformula, my prior experience with combined electronic systems, the work of Luce and Gill on low-dimensional chemistries, provoked the following series of questions. Can we find quantum mechanical solutions for an electron confined to a 2D region defined by the superformula? How do those solutions vary as a function of A, B, and N? Analytic solutions exist for some subset of A, B, and N, but what's the behavior outside of those regions? Now, how relevant is this work? How important is this work? Probably not, to be quite honest, but that's okay, as what's driving me to explore these questions is not a lust for fame or fortune, but just curiosity. I'm just interested in finding the answers to the questions because. So I set about creating an environment to determine numerical solutions to this problem, and I used the symbolic language tool Mathematica to do so. I wrote a small Mathematica notebook to define a region, so one described by the superformula and dependent on the parameters A, B, and N. The notebook evaluated the Helmholtz equation subsequent to the condition that the solutions vanish at the region boundaries. I made sure that the notebook plotted the resulting eigenvalues and eigenvectors so that I could see the energies in the wave functions. And I was obviously able to control the accuracy of the numerical solutions using an exposed parameter. This is a mesh spacing, delta. The resulting notebook is relatively compact and should be very, very interpretable. Okay, so what does this result in? Well, this results in a giant table of numbers. Here we examine as a function of n for constant a and b, the area of the region defined by the superformula with those parameters, and the ground state energy, that's the first eigenvalue, as a function of 3 ever finer mesh spacings. As we increase delta, the mesh spacing, we find that our results converge and our accuracy appears reasonable to roughly 5 decimal places. A couple of things to notice for this choice of parameters. As n tends to infinity, we are making the defining region more and more like a square. So we see the area of the square being 4 units for n equals infinity, while for n equals 1, the rhombus, we have an area of half of that. Notice also that for n equals 2, the area looks a little like pi. Not surprising when we recall that for n equals 2, the region defined by the superformula is a circle. As n tends to infinity, the area converges on that of a square of side 2. Here is the first eigenvalue, so E0, the lowest energy, as a function of n for the finest grid spacing. Just a reminder that for n equals 1, 2, and infinity, these are regions that are illustrated here that we know we have analytic solutions exist for the problem of an electron confined to those regions. The Mathematica notebook, as by definition, as I described it, will also generate the eigenfunctions associated with an electron confined to these regions. Here's a progression of these eigenfunctions as a function of n for constant a and b. I haven't explored the eigenfunctions in detail, but here they qualitatively confirm, or conform rather, to my expectations, with a central feature at the center of the region corresponding to a maximal localization of the particle. The eigenfunctions seem particularly interesting to explore degeneracies of excited states, but this isn't something I've currently looked into. For constant a and b, exploring these systems as a function of n, given that n tends to infinity, results in solutions to this problem corresponding to those of an electron in a square. We can use this analytic reference for both area and energy to further explore convergence. We seem to reach a numerical limit at around an n of 100, wherein we functionally reach something indistinguishable from a square, or at least at this level of numerical accuracy. The convergence with respect to the area appears to be a simple decreasing function. With respect to log n, the artifact associated with our solution at n equals 8 is also evident in the plot here too. So I'd done all of this work. I'd had some ad hoc conversations with other theoretical chemists who were supportive but acknowledged this wasn't exactly cutting-edge research because it's not clear outside of from a pedagogical perspective what insight this provides. So as a possible boon to chemistry educators, I worked this up into a summary which I presented virtually at the American Chemical Society meeting in the autumn of 2020. You can find this presentation, the Mathematica notebook, the data here on Figshare. Now, somewhat frustratingly, the meeting format was such that I had to record my presentation for others to view. as the American Chemical Society meeting is one of the largest scientific congresses, it summarily got lost in the void. It took me hours to create slides and summarize the work, and then again another hour or two to prepare the materials for presentation in the requested format, all for a total of a handful of scientists to sort of pay attention to. I had no feedback, no engagement, and it was really just a thing I did. So I fast forward 18 months, and my family and I have relocated to the UK to spend the summer of 2022 with my parents, and I received the following random note of outreach from Professor Gielis. Dear Dr. Thompson, I found a presentation in No Man's Sky, the Superformula, and the accompanying Mathematica notebook file. There are a few papers out there addressing the same. Are you still working on this or interested to continue? It's really made my week at the time, and really validated my participation in kind of open science, right? Doing something using the internet and hoping open access channels really allow for sharing and seeking the engagement and feedback of others. So this was a real treat for me. As I'm sure most of you know, Professor Gillis is extremely generous with his time, so we spoke both via Zoom and via email, and I've thoroughly enjoyed our interactions. I felt that with his input, we could work up the contribution into a solid resource for use by the community of educators in chemistry. So we did a thing. We submitted a publication both on ChemArchive, so the link here is shown at the bottom of the slide, and for peer review at the Journal of Chemical Education, a journal of the American Chemical Society. I really like this contribution, and I think it hangs together logically really very nicely, as does my harshest editor, my wife, who, in a completely out of character move for her, actually complimented us on this work. I should point out that she's a physician with a formal training in gastroenterology. Now, unfortunately, her sentiment wasn't shared by the editor of the journal, who summarily rejected it before even sending it out to reviewers, and called out specifically, quote, the lack of significant or rather sufficient pedagogical context to be useful to the readers of the journal, end quote. Now, getting rejected is no fun, but usually when you've had a moment to relax, maybe a drink or two, a nice walk, run, etc., the veracity of the comments and the feedback begin to ring true. Anyway, a couple of weeks later, we had friends visiting for lunch, a colleague of my wife's, her partner and their children. The partner is randomly an experimental chemist at a liberal arts university in New York, and I found myself describing this work and the recent rejection. And so, as we discussed a little more, it seemed that there might be an opportunity for a collaborative activity, as I could translate the work we'd done so far into a workshop of sorts or a tutorial, which could then be given to students who could then assess with respect to an objective set of learning measures. So I sent Professor Abernathy the submitted manuscript. He wrote to him one of his colleagues, a physicist with a chemistry leaning, and we worked this up as a module for inclusion in their physical chemistry teaching module. So students at Sarah Lawrence University have been introduced to educational material that provides background and context to the importance of particle inner box problems, both theoretical and experimental. It introduces them to the superformula, and it allows them to explore the particle in a superformula as a sandbox to understand the subtle interplay between analytic and numeric solutions to well-defined theoretical problems. So hopefully assessment and resubmission will follow in early 2024. Now, there are, of course, many possible steps for future work, including to continue exploring the zoo of possible shapes as a function of these tunable parameters, to explore in more detail the excited states and degeneracies as a function of these parameters, and finally, of course, to consider the case of n greater than 1. This is actually a very robust research project in and of itself that's at the moment outside of the scope of the current time I have available, but still of interest to note. Finally, I'd like to quickly introduce you to the Danish polymath Piet Hein. He gave the superellipse its name. However, he wasn't its discoverer. He was an advocate of the superellipse in design and even created an award-winning roundabout using it. He's also the inventor of the Soma cube, 8 shapes that can be combined into a cube or in one of 240 different possible ways. Apparently, the idea for the Soma cube came to him during a lecture on quantum mechanics being given by Werner Heisenberg in the 1930s. I found out all of this when I was gifted a Soma cube by my sister around the time I started all of this work, and I thought it was quite interesting that it had another random connection to the superformula that I'd just become familiar with. With that, thank you so much for your time. If you have any questions or thoughts on this work, please don't hesitate to reach out. And before concluding, I'd just like to give a special thanks to Mr. Chachadorian, he's a staff writer at the New Yorker, for writing such a compelling profile of No Man's Sky. For Professor Gillis, obviously, for reaching out, answering the call into the void, and everything that's followed. Professor Andreas Seller, he's a professor in organic chemistry at University College London, who took the time to answer my random email question regarding an experiment he'd made me do, which involved solvated electrons. And then Professors Abernathy and Frey for their collaboration and willingness to bring this material to their students. And then finally, my sincere thanks to you all for your time and attention in listening to this material.